Our lesson on 5.3 is a technique that we can use to solve certain types of quadratic equations, and it's going to be the technique of just finding the square root. So first, I'm going to review for you. At the top of your paper, you're going to see a list of the first couple perfect squares, 1, 4, 9, 16, 25, etc. And we need to think about how we're going to reduce radicals. Now, before we did this lesson, we should have done a worksheet on reducing radicals and just knowing how to do that. So hopefully you have that under your belt, but if not, let's try a few examples here. So number 1 says the square root of 24. So I need to look at my list of perfect squares and decide which one is the biggest number that will divide into 24 evenly. So I find out that 4 is the biggest one in that list that'll divide into 24 evenly. So we're going to change the square root of 24 to say the square root of 4 times the square root of 6. And then we can rewrite the square root of 4 as a 2. So our final reduction of this square root is 2 square roots of 6. Now eventually you won't have to show me all that work to reduce the radical, but for now you're going to have to show a little bit of work. So for the square root of 12, again you look at the list of perfect squares and decide who's the biggest perfect square that will divide into 12 evenly, and again that's going to be 4. So this is really the square root of 4 times the square root of 3, and we're going to rewrite the square root of 4 as a 2. So our final answer is 2 square roots of 3. Square root of 48. Now there are several different perfect squares that you might think of. The first one on the list is a 4 that will divide into 48, but that's not big enough. Remember, you have to find the biggest perfect square that will divide into 48 evenly. So it turns out 48 is going to break down into 16 times 3. And then we know the square root of 16 is really a 4. So the square root of 48 comes out to 4 square roots of 3. And then the square root of 28, the biggest perfect square that's a factor of 28 is 4. So we have the square root of 4 times the square root of 7. But of course the square root of 4 is a 2. So our final answer is 2 square roots of 7. Now those were just simplifying radicals. They were not solving any equations. That was just us warming up on how to simplify a radical. Let's continue on. The square root of 52. If I think about the biggest perfect square that will divide into 52 evenly, I think that's a 4 times a 13. And then we know that the square root of 4 is really a 2. So our final answer is 2 square roots of 13. Now when you have a division problem, what we can do is we can break this radical to say it's really the square root of the numerator over the square root of the denominator. And the reason we did that is because sometimes they reduce. For instance, right here, the square root of 4 is really a 2, not square root of 2, but just 2, and the square root of 9 is just a 3. Now when we get to number 7, we're going to start the same way. We're going to break it up into the square root of the top numerator over the square root of the denominator. Unfortunately, neither one of those break down. And even more unfortunate, we're not allowed to leave square roots or any sort of radical in the denominator. So we're going to do what's called rationalizing the denominator. So what I want you to do is look at what the denominator is, and it's a square root of 3, and we're going to multiply both the numerator and the denominator by the square root of 3. The reason you have to do it to both the numerator and the denominator is because the square root of 3 over square root of 3 is really the same thing as multiplying by a 1, so we're not changing the value of this problem at all. So now when I look at my numerator, I have square root of 2 times square root of 3, which is the square root of 6. But my denominator becomes the square root of 3 times the square root of 3, which is the square root of 9, but that simplifies down to the number 3. So you'll notice our whole goal there was to get rid of the radical in the bottom, and we did just that. And I want you to be careful here. This is the square root of 6 over 3. Those do not reduce. Radicals and whole numbers cannot reduce because the square root of 6 is not a 6, so it cannot be divided by a 3. We're going to do the same sort of idea here in number 8. We're going to start with the square root of 6 over the square root of 11. But then we can't leave our answer like that. We have to rationalize the denominator. So I'm going to multiply top and bottom by the square root of 11. And I kind of ran out of room, so follow me down there. Up in the numerator, the square root of 6 times the square root of 11 is the square root of 66. And then square root of 11 times the square root of 11 is just an 11. Okay, moving on, we're now going to solve some equations by taking the square root. Now here, because we are solving an equation, Anytime you take the square root in an equation, you need to add a plus or minus to whatever the simplified answer is. So for instance, on number 9, we're going to square root both sides, and we're going to get x equals, now instead of just saying 4, the answer is also a negative 4. So we're going to write it as x equals plus and minus 4. When I get to number 10, before I start square rooting, I have to get rid of our coefficient of 2. So I'm going to divide both sides by 2, leaving us with x squared equals 25. And then when you square root both sides, you're going to have to give me both answers. X equals plus and minus 5. And that's only true for solving an equation with a square root or any even root. Okay, on number 11, we're going to subtract the 1 from both sides before we do anything with the square root. So we have 2x squared equals 7. And then I'm going to divide both sides by 2. Now, I know this is not the greatest answer, but that's okay. We have x squared, equals 7 halves. Now, when you square root both sides, I'm going to use the technique where we square root the top and the bottom, the numerator and the denominator. And we're not going to quite be finished with our answer for a little bit of time here. Remember, we're not allowed to have radicals in the denominator. So I'm going to need you to remember how to rationalize. We're going to multiply the numerator and the denominator by the square root of 2, leaving us with the answers of, remember, plus or minus. Up in the numerator, we've got square root of 2 times square root of 7, so square root of 14. And then in the denominator, square root of 2 times square root of 2 is just a 2. And same issue that we ran into before, some children think they're supposed to divide 14 by 2. The square root of 14 cannot be divided by a 2, so that's our final answer. On number 12, our first step is to add the 5, so we have x squared over 3 equals the 12. And then to get rid of the divide by 3, we're going to multiply both sides by 3. So we have x squared equals 36. And now when you square root both sides, we get our answers of x equals plus n minus 6. Okay, moving on to another type of problem. This time, instead of just having x squared, we have a quantity squared. So once we get to the point where the parentheses set, the quantity is isolated, then we're going to go ahead and take the square root. So on number 13, first thing I have to do is do the opposite of a 1/3, which is multiply by 3. And we end up with quantity x plus 5 squared equals 21. Now at this point we're stuck. We can't do anything until we get rid of that squared. So I'm going to go ahead and square root both sides of the equation. So on the left hand side we still have x plus 5. But on the right hand side, because this is an equation and we just took a square root, you have a plus and minus. And then the square root of 21 does not reduce at all because there's no perfect squares inside of 21, so it's just the square root of 21. And then our final answer, as strange as it looks, all you would have to do is subtract the 5 to the other side. And since we can't combine a negative 5 and a square root of 21, our answer is written as negative 5 plus and minus the square root of 21. So if you can't combine the terms algebraic or mathematically, you're just going to write them in this notation. Okay, our first step in number 14 is to divide by that 5 before we begin. So we have the quantity x minus 1 squared equals 10. So same issue we run into here. I have to get rid of that squared, so we're going to square root both sides. And on the left hand side you now just have x minus 1 equals, because we took a square root in an equation, the answer is now a equals plus and minus square root of 10. It stays square root of 10 because it doesn't reduce at all. And then your final answer is just to add this 1 to the other side. So it becomes x equals 1 plus and minus the square root of 10. There are two answers there. They're just really gross decimals if we typed it in, so we're going to leave it in exact form. Okay, our next problem, to get rid of the 1/2, we're going to multiply both sides by a 2. So you end up with quantity x plus 8 squared equals a 28. Now I need to get rid of the square root, so I'm going to square root both sides. And here we have something else to think about. We have x plus 8 equals plus and minus. We need to think about how to reduce the radical of the square root of 28 because that is something we can reduce. So 28 can break into 4 times 7. And if I think about reducing the square root of 4 times square root of 7, that becomes 2 square roots of 7. So my final answer, once I subtract the 8 to the other side, is negative 8 plus and minus 2 square roots of 7. Alright, so as weird as those answers look, they're actually really pretty, in a math teacher's point of view at least. Moving along, some more of the same, so just if you need some more practice on this, continue with me, otherwise move ahead. The square root of 18, we're going to break down by saying it's really the square root of 9 times the square root of 2. I always put the perfect square first because that makes my reducing really, really easy. So that ends up being 3 square roots of 2. The square root of 32, the biggest perfect square that we can divide 32 by is a 16. So 32 is a 16 times 2. And then when I reduce that radical, I end up with 4 square roots of 2. Ooh, 98, that's a thinker. I'm thinking 49 times 2. So we can break that into the square root of 49 times the square root of 2. But the square root of 49 is really a 7, so our final answer is 7 square roots of 2. And then when you get to number 19, we're going to break it into the square root of the numerator over the square root of the denominator. Now technically the square root of 1 is a 1, so I could change that right now, but I have a bigger issue, and that's the rationalization of the denominator. I got to get rid of the radical in the denominator, so I'm going to multiply both the numerator and the denominator by the square root of 3. And that's going to give me square root of 3 in the numerator, and then 3 in the denominator. Alright, moving on. Some more practice here for us. Number 20, we're going to add the 1 to both sides and get x squared over 25 equals 12. Now to get rid of the divide by 25, I'm going to multiply by 25 on both sides, and we're going to get x squared equals 300. And now when you square root, 300 can break down, so we got to think about that for a second. We're going to have x equals, I'm going to go ahead and put down the plus or minus so I don't forget that part. 300 breaks into 100 times 3. So when I reduce that radical, I end up with plus and minus 10 square roots of 3. Okay, on number 21, before I begin, I'm going to divide both sides by that 4. A good question would be, well, why don't you try to distribute into that parenthesis? Well, you have to remember x minus 1 quantity squared is not x minus 1. It's really a FOIL problem. So you can never distribute into something that has an exponent raised to it like that without first simplifying. And trust me, you don't want to do that. So we have quantity x minus 1 squared equals 25. Now this is a unique case. We're going to square root both sides. And the last few problems we did that were like this had kind of gross radicals off to the side that didn't reduce. Well, this time, square root of 25 ends up being equals plus and minus 5. So a lot of us are going to think we're done when we write down 1 plus and minus 5. But since there's no longer a radical in the problem, you can actually tell me my two answers. The first answer would be 1 plus 5, which is 6. And the other answer would be 1 minus 5, which is a negative 4. So if you have no more radical left in the problem, I need you to continue on and actually give me your two answers. So here for number 22, there's no coefficient, so I'm just going to go ahead and square root both sides. And again, we have a case where we end up with something that simplifies. So we have 2x minus 5 equals plus and minus 9. Now, I'm going to pretend like I can't simplify it for now. I'm going to add the 5 to both sides. And then I'm going to divide both sides by 2, kind of like a quantity. So I have x equals, now let's think about this because there's no more radical, so I can actually figure this out. 5 plus 9 is a 14, divided by 2 is a 7. And then 5 minus 9 is a negative 4, divided by 2 is a negative 2. So think about continuing your work if there's no more radical left at the end of the problem. Alright, a little bit of trouble going on here in 23. We've got a couple different places where I see x squared in the problem. So I need to bring those x squareds together And I'm going to go ahead and subtract the 2x squared over to the right hand side. And at the same time, I'm going to go ahead and add this 5 to the left side. So we end up with 8 equals 2x squared. Now before we square root both sides, I'm going to divide by 2. And I end up with 4 equals x squared. Well, that's not that bad. Square rooting both sides. Be careful that you don't forget your plus or minus. 2. Alright, moving along, number 24. Let's get rid of that 1/2 before we do anything with the square root by multiplying both sides by a 2. Those will cancel. So we have quantity x minus 4 squared equals a 16. And now when I square root both sides, I get x minus 4 equals plus and minus 4. Now again, I'm going to start by adding the 4 to the other side, and you can't stop there because we no longer have radicals. You need to tell me your two answers. So x equals 4 plus 4, which is 8, and x also equals 4 minus 4, which is 0. And there they are. Okay, a little bit of application problem. When we drop an object, we're going to see that its rate of decrease has an acceleration, and that's due to gravity. So we've seen this equation on our last lesson on 5.2, and I made you solve these problems using factoring methods. Well, we're going to use the same equation, except now I'm going to have you solve this using square roots. So I want you to think about this as the equation we're going to use. This is your final height, which normally for these problems means we're going to fall to the ground, but not always. T is time, usually in seconds. And then h sub naught, anything with a 0 subscript, means initial. So h sub naught would be the initial height. So our problem involves a stuntman. He's going to fall out of a window that's 100 feet above the ground. That's probably an important number. The cushion that he's going to fall onto is 26 feet wide, 30 feet long, and 9 feet high. Since I'm only interested in height, I think the 9 feet high is the only part I'm interested in there. The question is, how many seconds will the stuntman fall before hitting the cushion? So using our formula, which is listed at the top here, our final height after the stuntman drops to the cushion, let's, neglect to think about the cushion falling down. Let's just say it's 9 feet high. That's 9 equals negative 16. I don't know the time. That's what I'm going to look for. And then my initial height for the stuntman, where he jumped from, was 100 feet up. So if I'm going to solve this problem, I'm going to go ahead and I'm going to subtract 100 from both sides. I'm going to get a negative 91 equals negative 16t squared. Now I'm going to have to do 2 more steps. I'm going to have to divide by a negative 16. And I don't really know what decimal that comes out to because I don't have my calculator in front of me. But the last thing I'm going to have to do is I'm going to have to square root both sides. So once I take negative 91, divide by negative 16, and square root, I think I get an answer of approximately 2.38. So the stuntman is going to fall for roughly 2.38 seconds. Now the reason I didn't put a plus or minus is because this is a real-life application. It doesn't make any sense to say that he's going to fall for negative 2.38 seconds. So a movie camera operating at a speed of 254 frames per second is going to record the fall. How many frames of film are we going to need to use to show this fall? Well, since it's 2.38 seconds, and every single second is 254 frames, I think we're going to take the 2.38 and we're going to multiply it by the 254 frames per second. And when I do that, it comes out to, I should say approximately, so a little squiggly sign, 606 frames. Probably something important to know if you're the person in charge of setting up the film and making sure you're not going over budget. Okay, same formula. They use S here instead of H sub naught, but it works the same way. This time the object is going to hit the ground, and we're going to drop it from 2 different heights. First 100 feet and then 200 feet. And then the question at the very end says, does the object that's twice as high take twice as long to reach the ground and explain. Well, after we do the math, we're going to see what happens. So for the first problem, remember the final height is it's on the ground, so that's going to be a 0. So it's 0 equals negative 16 t squared, and then our initial height is 100. So I'm going to add the 16 t squared over here. And then before I square root, we're going to divide by 16. So we can cancel those out. And let's see, I get t squared equals 6.25. And then when we square root both sides, whoop, I get roughly, or exactly, 2.5 seconds. Now when I do the same thing for an object at 200 feet up, so I'm going to add the 16t squared over. I'm going to divide by 16 on both sides. And you get t squared equals 12.5. So then last step here, we're going to square root. And we get roughly, or exactly, 3.5 seconds. So did it take twice as long for the object to reach the ground? No, it did not. And the explanation for you at this level could just be, you know, when I worked out the math, a 100-foot drop took 2.5 seconds and a 200-foot drop took 3.5 seconds. That's fine. But the reason it doesn't have that sort of a relationship is because this is not a linear equation. This is a quadratic equation. And gravity is an acceleration force. So you're going to see that it doesn't speed up in a linear, or what most younger students would see as a pattern. It's not going to be, you know, a slope of any sort. This is quadratics, totally different explanation, a totally different relationship. So however you want to write that down in your notes, go right ahead. All right, I think that concludes our lesson.